Hi, I'm Chris Muchler, Principal Enterprise Architect and VCDX 257 from virtualelephant.com. Today, I am going to deep dive into the world of TCP/IP packets with Module 3 of the Network Fundamentals course and help you understand why packets are so fundamental in networking. Let's get started. In Module 2, we covered the fundamentals of TCP/IP, but what exactly are TCP/IP packets? Well, to put it simply, they are the building blocks of data transmission in computer networks. And just like letters in an envelope, packets are the units in which data is sent and received across the internet and local networks. But you may be asking yourself, why are these packets so important? Well, in the world of networking, data is often too large to be transmitted as a single piece, and so it's broken down into smaller packets for efficient and reliable transmission. These packets can travel separately across the network, taking different routes, and then be reassembled at their destination. And this division into smaller packets ensures that even if some packets get lost or delayed during transit, your data can still be successfully reconstructed at the destination. TCP/IP packets are like the bricks used to build the internet, and without them, data couldn't travel smoothly from your device to a server on the other side of the world. And understanding how they work is crucial for anyone interested in networking, whether you're a beginner or just looking to deepen your knowledge. As we get started with Module 3, the first thing that we're going to talk about are Ethernet frames. Ethernet frames are the foundation of local area network or LAN communication. They are going to define how data is packaged, addressed, and transmitted over Ethernet networks. So let's break down the key components of an Ethernet frame and understand its roles. So first, as you can see on the graphic here, we have the preamble. And every Ethernet frame starts with a preamble. This is a sequence of bits used for synchronization and timing purposes. Moving on from the preamble, we have the destination and the source MAC addresses. Now, the destination MAC address comes next, and it's a unique identifier for the recipient device. And like I told you before, the MAC address is a hardware address that's usually on the card or on the port, and it's hardwired to that device. And when a frame arrives at a switch or router, this address is going to help determine where the frame should be forwarded to. And then we have the source MAC address. Following the destination MAC address is the source, and this is going to identify the sender of the frame. And it's crucial for devices on the network to know who sent the data. The next part is the length, and this field is going to specify either the type of data being carried in the frame or the length of the frame's data portion. And it's going to tell the receiving device how to interpret the contents. After that, we have the data section. And the data section contains the actual payload of the frame. Now, this is where your message or file is going to actually be carried. And the size of this section can vary, but it typically ranges from 46 to 1500 bytes. And we're going to talk more about the size of the data frames in a few moments. After that, the final part is the frame relay check sequence, or FCS. And finally, this field, or the CRC, the cyclic redundancy check value, is going to be used for error checking. And when the frame arrives at its destination, the receiving device is going to check this value to make sure that the frame wasn't corrupted during the transmission. This goes back to TCP as a whole being a reliable transmission protocol so that we know our packets get there in the way that we intend them to get there and haven't been corrupted. So why is understanding Ethernet frames important? Well, it's going to form the basis for how data is organized and transmitted across your network. So whether you send an email, watch a video, or browse a website, data is going to be broken into these frames and transmitted over Ethernet and then reassembled at its destination. So a properly formatted Ethernet frame is going to ensure that the data arrives intact and is delivered to the destination. And any misconfiguration or error in these frames can lead to communication problems, network congestion, or security vulnerabilities. Now, as we delve deeper into our networking journey, keep in mind that Ethernet frames are fundamental building blocks of your local network. and they facilitate seamless communication between devices, and understanding their structure is key to becoming a network expert. Now let's visualize your TCP/IP packet as a tiny digital courier that carries your data across the vast network landscape. And to do its job effectively, each packet consists of two main components, the header and the payload. Now you can see on the graphic on the screen how it breaks down into the different high-level parts of a TCP/IP packet and how those parts correlate back to the OSI model layers that we discussed in Module 1. And again, understanding the OSI model is going to be crucial as we dive deeper into the network concepts and everything that goes into them. The header itself is like an envelope that contains critical information about the packet's journey. It includes details like the source and destination IP addresses, which tell the network where the packet's coming from and where it's going. The source and destination port numbers, on the other hand, help the receiving device determine which application or service should handle the data. In addition to these, we have sequence numbers and acknowledgement numbers that play a pivotal role in ensuring data arrives in the correct order and that both sides of the communication are in sync. And we talked about this in Module 2 around the TCP handshake. And so you can see here on the screen that we have certain control flags like the SYN and the ACK, which are signals on the packet indicating the beginning and the acknowledgement of a connection. Now finally, we come to the payload itself at the bottom of the graphic, and that's where your actual data itself resides. Now think of this as the letter inside the envelope. It carries the message, the file, or whatever data you're sending and receiving. Understanding this structure is crucial because it allows network devices to process and route packets across the network efficiently. And so when a packet arrives at a router or a switch, it's the header information on the screen that guides it to its next destination. Now, once there, the payload is going to be delivered to the appropriate application or service running on the remote device. And so as we move forward in this module, remember that the header and the payload of a TCP/IP packet are like the DNA of the network communication. And so those two pieces combined are going to contain the instructions and data that ensure that your messages reach their destination accurately and securely. Now, as we move on, the next thing that we're going to discuss is how a packet actually traverses the network. And so we're going to look at this journey and break down all 15 steps in this animated slide. The important thing to remember here is that things are going to happen on one end and then happen in reverse on the other end. And so the first step that happens is this application data generation. This could be anything from a simple text message to a complex file transfer. Now, once the application has generated the data, the next thing that's going to happen is data segmentation. Now, this is where large chunks of data are segmented into smaller, manageable pieces by the transport layer. And think of it as slicing a cake into individual pieces that make it easier to eat. Once that's done, the next part is the transport layer protocol. And this is going to be either TCP or UDP, as we've talked about before. One of these protocols is going to be leveraged, and it's going to ensure the data integrity and the proper delivery of the data itself. Now, once that's happened, the next thing that happens is a port number assignment. And these port numbers are assigned to the different data segments, helping the destination device know which application on the other end should receive the data. Now, following the port number assignment, the next phase is segmentation. And again, the data segments are going to be further divided into smaller parts or smaller units known as packets. Once that's done, then we're going to get an IP address assignment. And each packet itself is assigned an IP address, which serves as a unique identifier, as we've talked about in the vast network landscape. Think of it as your street address when you're mailing a letter. Once that's done, a routing decision is going to happen. Now, this is going to be a critical moment because routers are going to make decisions on the best path for the packet to reach its destination. We're going to talk more about how those best paths are determined in our BGP and our routing modules later on in the course. Once that's done, the packet is going to become encapsulated. And like placing the letter in an envelope with headers containing the routing and addressing information, it's all going to be packaged up nicely. At this point, transmission happens, and the packet's actually sent out across the network from the client destined for the server address. And so this packet is going to start its journey across the network, whether it's a LAN or a WAN across the internet. It's going to traverse different routers, switches, and cables, physical mediums, until it gets to its destination. Now, along the way, it might not take the most direct path, and so there are going to be some intermediate routing that's going to take place. And this is going to basically hand off the packet as it goes from one address to the next until it eventually gets to its destination. And that's the next step. The packet is going to arrive at its destination where the receiving device is going to get the packet. So we're almost there at this point. Now, essentially, we're going to do everything in reverse order. So first thing that we're going to do now on the other end of this packet traversing the network is decapsulation. We're going to start to reveal what's inside that payload itself, at which point then we're going to have the delivery. So the packet is going to actually arrive at the destination device, and then it's going to become ready for whatever further processing the application or service needs to do on it, at which point there'll be some transport processing. Now the transport layer, right, TCP or UDP, is going to basically reassemble and verify all the data segments got to the other end as intended. At which point, the final thing is the application and data processing is actually turned over to the application itself to do with whatever it might be, display a web page, process a text message, whatever. And there you have it. This is a comprehensive journey of a TCP packet, TCP/IP packet, from its inception in an application to its ultimate delivery and processing at its destination. And again, understanding how all of this works in totality is going to be very crucial for you as you go through this process of understanding how packets traverse the network. So you've heard me talk about already breaking up the payload into multiple packets or chunks so that it can be transmitted more efficiently across the network. So we're going to dive into how that happens right now. The MTU, or maximum transmission unit, is the largest amount of data that can be sent in a single packet. And so this is going to refer to that maximum size that can be transmitted over a specific network segment without being broken up into different pieces. And so different network technologies and types are going to have different MTUs. For example, now Ethernet, which we're going to be most familiar with, typically has an MTU of 1500 bytes, while other technologies like DSL or ATM have different values. Now, when a packet size exceeds the MTU of a network segment it needs to traverse, it has to now be broken up and fragmented into smaller packets that are going to fit within that MTU value. Now, this process is going to ensure that data can move smoothly across networks with varying MTUs. Now, on the flip side of MTUs, if you want to go above a certain value, this is where jumbo frames come into play. And jumbo frames are becoming more and more commonplace in our networks. And so jumbo frames are a networking feature that allows larger MTUs compared to the standard frames of 10, 15 years ago. Now, while standard Ethernet frames typically have an MTU of 1500 bytes, jumbo frames can have MTUs ranging from 9000 to 9216 bytes. And some of the benefits of leveraging jumbo frames in your network architecture include reducing your overhead, lowering your latency, increasing your throughput, and allowing for better CPU utilization on your network devices. However, there are some challenges to consider when you're thinking about enabling jumbo frames inside of the network. There can be compatibility issues because not all networking equipment supports jumbo frames. And so interoperability issues can arise if there are varying MTU configurations on your network. So this is going to be something important to consider if you're migrating from a brownfield environment versus building out a new greenfield network. And MTU mismatches can lead to packet fragmentation and loss that you weren't intending to occur, which can then negatively impact your network performance. Now, in the world of software-defined networking, which we're going to cover in more detail in Module 8, MTU mismatches are like DNS configurations in a virtual world. If you're experiencing weird behavior on the network with a software-defined network, the first thing that you're going to want to do is check your MTU settings first. Now, the second half of this is packet fragmentation. Now, packet fragmentation that we've talked about is now a mechanism that allows this large amount of data to be divided into smaller, more manageable segments for transmission over the network. These smaller segments, called fragments, can traverse the network independently and then be reassembled at their destination. It's like taking that large document, dividing it into multiple pages, sending each page individually, and then having the recipient on the other end put all of those pages back together to reconstruct the original document. Now, understanding packet fragmentation and MTUs is crucial for network administrators, as it impacts the efficiency and reliability of data transmission. It's like knowing the limitations of your vehicle's cargo capacity before moving goods across long distances. And I had to do this a couple years ago when I took an overlanding trip from Colorado to Alaska. I had to know just how much could I actually shove in the back of my Tacoma to be able to get us from point A to point B. And so what you see here on the slide is a demonstration of how a larger packet at the top is broken up and fragmented into multiple pieces to ensure that the entire payload is transported across the network. Now, the next thing that I want to cover in this module is on packet capturing and analysis. And packet capturing is going to need to become a fundamental skill that you have as a network engineer, a network administrator, or even a network architect. And so because it is such a fundamental skill, I'm going to show you how to use a tool like Wireshark to perform packet capturing and analysis. So before we dive into Wireshark, first, let's answer the question, what exactly is packet capturing? Now, it's the process of capturing packets as they traverse a network or go across your network. And just like intercepting letters in the mail, packet capturing tools grab network packets in real time, allow you to see what's happening on the network. So kind of think of this as eavesdropping on the conversations happening between two devices. Now, why is this ability important? Why do we want to actually do packet capturing? Well, capturing packets is going to provide you as a network administrator with a wealth of information. It's going to allow you to monitor network performance, identify network issues, and even detect security threats. It's a bit like having a CCTV camera in your network recording every packet that goes by. And over time, these tools have gotten much better. So packet analysis is the flip side after you capture it. And with packet analysis, this is where the real magic is going to happen. So after you've captured these packets, you're going to use an analysis tool like Wireshark to inspect and dissect them. So it's going to be like examining the evidence in a case. You can see who's communicating with whom, what data is being exchanged, and even spot anomalies or problems in your network. For example, if you're troubleshooting a slow network, packet analysis can reveal which specific applications or devices are causing the bottleneck. Or if you're concerned about security, it can help you identify unusual or potentially harmful traffic patterns. And so by understanding packet capturing and analysis, you're going to gain the ability to diagnose network issues, optimize performance, and enhance security. It's like having a magnifying glass to zoom in on the network traffic, revealing the hidden details you need to make informed decisions. Now, as we jump into Wireshark itself, and I show you a demo of me capturing packets across my own local area network, this is going to be a pretty high-level walkthrough. So I encourage you to download Wireshark on your computer and start playing with it. Find other courses on YouTube, which I will link below, that will provide you a more in-depth training to be able to leverage Wireshark within your environments. All right, so now we're going to jump into Wireshark, which you can see here on the screen. I'm going to show you real quick a web browser. So I have Chrome running. This is a view into my home lab that's running a bunch of different stuff, but it's generating a lot of traffic. Now I have a dedicated NIC feeding into my home lab environment. So when we do the packet capture in Wireshark, we'll only be seeing traffic that's going between my desktop machine and my home lab that I have running in a closet. So I'm going to switch back to Wireshark. So once you've downloaded Wireshark, you'll see a screen similar to what you have here on the video. You can see that it's seeing some traffic already, and you can see that it's listed out all of my different devices that I have. So everything that is connected to my home lab is on this Ethernet. As you can see, as I hover over it, it's showing that my address of my local machine here is 10.1.10.5. So we're going to go ahead and double click on this. And then as soon as we do that, it's actually going to start capturing packets. Now, one of the things that Wireshark allows you to do is actually filter. So right now what you see scrolling across the screen are actual packets between my desktop and some lab systems that I have running. And so as I showed you that I have that Chrome window open. So what we're going to do is we're going to apply a filter, and we're going to type in HTTP. You can see here that it starts to auto-populate some things for us. So we're going to do that and then start to filter just HTTP traffic. And then if I go into my Chrome window and I click here, you can see there was some stuff that scrolled across. And we're going to come back to this in just a moment as we dive a little bit more into it. So one of the great things that Wireshark allows you to do is, obviously this is a live packet capture that you're able to do. But one of its strengths is that most Linux systems, there's a tool called TCP dump, and that's really what's running behind the scenes here that you see on the screen through Wireshark as a UI. You can run TCP dump on a network device. You can run it on a Linux machine. So depending on the issue that you're troubleshooting, like we said, you can eavesdrop on this conversation that's going on in your network. And so you can run TCP on a couple different locations to be able to capture the packets. You can save that packet capture to a file using TCP dump. And once you've saved the file, you can actually import it here into Wireshark. So as soon as we hit stop here, we're going to stop capturing the packets. That allows us to save it. And so now we can go back, and if you have other packet captures, you can copy them over here, and using the file menu, you can open one of the capture files that you've captured elsewhere. And then you can go back and actually look through to see what your issue was that you were having. So that's amazing. So once we've captured the packets, right now, we talked about a moment ago, the real strength is in the packet analysis and being able to see what's going on. So what you can do here is, you can see I have some Cisco devices. There's some other things running on various networks within my network. And as soon as you click on one of these, you can see a little bit more information. So you can see the frame information here. Okay, you can see how big the frame was on the wire. You can see the interface that it came across. You can see the destination MAC address there and the source MAC address here, right? So destination, source, and then one of the nifty things that Wireshark does is on the right side of the screen, it shows you where that information was kept. So you can see 001201 D4 E4E48. That's the source address, source MAC address for the device that this was talking to. So this, if I'm not mistaken, is probably one of my Catalyst switches. You can see the Internet Protocol version 4, not V6, so IPv4. You can see the source IP and the destination. This was just a hello packet that was going across, and it was UDP, so you can see user datagram protocol. So one of the things that Wireshark lets you do here is you can see that there's all sorts of fields at the top: the number, the packet, the time, source, destination, protocol, length, and then some info. So if you're looking for something specific, you can go through and you can filter by, say, protocol. So you can see all of the DNS requests going across my home lab network at any given time. So as we look at the packet capture that we have and the data that I was able to grab, when we want to start to see some of the traffic, maybe in walk through a conversation over the network that was happening. So you can see here that I've highlighted this communication. So my source address for my local machine, 10.1.10.5, my destination address for my vCenter server, 10.1.10.11. Okay, so you can see here, it was number 99. It was the 99th packet that I captured. Timestamp, right? Source, destination, protocol, and then length, and then some application data. And so what you can do is you can actually walk through, okay, the conversation. So you can say next packet, takes you down to the next one, right? You can use the hotkey if you want, control, okay, and then you can walk through the conversation so that you don't have to get bogged down by all of the extra data that was going on. So you can see as we walk through, there's a conversation back and forth between my desktop machine and the vCenter server as it sends the data. And you can see in the bottom part of Wireshark, it's updating the information that it has for it. And so this is a great way for you to be able to figure out what was going on in your network. How are you communicating with something? Obviously, if there was a problem, you'd be able to detect it because you'd either not see the two-way conversation happening across the packet capture. So again, Wireshark, great tool to be able to leverage for both packet capture and packet analysis. It allows you to run it locally on a laptop, on a virtual machine, what have you. It lets you capture packets from that local machine, save them to a file. It is also able to then ingest a PCAP file that you've used or created from a TCP dump somewhere else on your network to be able to bring it into Wireshark to be able to visualize the data that was going on in your network. So that concludes Module 3 on packets. We've gone over what a packet is, the different components that make up a packet, how a packet traverses the network from a source to a destination, as well as being able to leverage tools like Wireshark and TCP dump for packet capture and packet analysis. Now in the next module, Module 4, we're going to jump into switches, and we're going to cover all things related to L2 and switching within your network. Now, if you've liked this video and you're enjoying this Network Fundamentals training course, please make sure that you like and subscribe to my channel. And please make sure that you also enable notifications and let me know what you think in the comments. I look forward to seeing you next time.